Welcome, friends. Today we will discuss the topic of advanced verilog interview questions and solutions. In hardware world, verilog is the primary hardware description language. To clear an interview for a job that requires verilog, one must be thoroughly familiar with the concepts. I have tons of industry experience to guide and discuss this topic in detail. Please subscribe to my channel. Please comment in the comment section if you have any questions. Thank you. With the introduction. What is Verilog? Verilog, standardized as IEEE 1364, is a hardware description language used to model electronic systems. It is most commonly used in the design and verification of digital circuits at the register transfer level of abstraction. It is also used in the verification of analog circuits and mixed signal circuits, as well as in the design of generic circuits. Next question. What are the advantages of using Verilog? Verilog language is concurrent in nature. That means you can have multiple events proceeding at the same time. It's independent of technology. It is robust and flexible, easy for designing and debugging gazillion gate designs. Gazillion in the sense the designs can be millions, billions of gates. Much better useful than manual schematics, and it's very efficient when it comes to large circuits. It is used widely and effectively in the semiconductor industry, extremely faster design and verification cycles. Okay, the digital design field is quite huge and diverse. This means the problem types and the varieties is also very huge and requires intense knowledge and a lot of hard work to solve them. So now let's jump into advanced Verilog interview questions. I'm assuming that the viewers have basic understanding and knowledge of Verilog. So the first question is, what is Verilog stratified event queue? So this diagram explains the Verilog stratified event queue. An examination of the diagram helps to explain how Verilog blocking and non-blocking assignments function. The stratified event queue is logically partitioned into 4 distinct queues for the current simulation time and additional queues for future simulation times. So the 4 segments are the active events, inactive events, non-blocking events, and monitoring events. The events that are included in the active events are the blocking assignments, evaluate RHS of non-blocking assignment, continuous assignments, $display command execution, evaluate input and change output of primitives. The events inside the active events, they can be scheduled in any order. Then we have inactive events, which is the #0 blocking assignments. Then non-blocking events, which is updating the left-hand side of non-blocking assignments. And the last one is the monitor events, which is $monitor command execution and $strobe command execution. So upon careful study of the sequence of these events and how they are processed, we can clearly understand how the blocking and the non-blocking statements are executed in any Verilog simulation. Next, we will discuss the coding guidelines. Efficient coding and design styles can be immensely helpful for any digital designer. These guidelines ensure that the design behavior matches the specifications. These guidelines are also a result of countless design, debugging, testing, evaluation, and experiences, and also feedback from billions of functioning products. So the first guideline is when modeling sequential logic, use non-blocking assignments. The sequential logic is flip-flop based logic. So when you are writing the design for a flip-flop, use non-blocking assignments. The number 2 is when modeling latches, use non-blocking assignments. Latches are also memory elements like flip-flops, so use non-blocking assignments when writing the code for latches. And number three is when modeling combinatorial logic within an always block, use blocking assignments. So combinatorial logic is regular logic gates without the latches or the flip-flops. So when writing the code for the regular gates, use blocking assignments. Guideline number four is when modeling both sequential and combinatorial logic within the same always block, use non-blocking assignments. Suppose you have to mix sequential and combinatorial within the same always block, always use non-blocking assignments. Guideline number five, do not mix blocking and non-blocking assignment in the same always block. It is self-explanatory that you do not mix blocking and non-blocking assignments in the same always block because it is tough to read and also prone to bugs. Guideline number six is do not make assignments to the same variable from more than one always block. So when do not make when multiple drivers to the same net exist, then the synthesis also gives you a warning. Guideline number seven, use $strobe to display values that have been assigned using non-blocking assignments. And then the last guideline number eight is do not make assignments using the count zero delays. So friends, these are very critical guidelines which really help to minimize the bugs in your design and also bring your Verilog code as close as possible to the actual synthesized hardware behavior. The next question is, does using $display command with non-blocking assignments work? So the non-blocking assignments are updated after all the $display commands are executed when we refer back to a stratified event queue. If you look at the sample code here we have uh, one blocking statement, a is equal to 0 and followed by a non-blocking statement of a is equal to 1, right? And when we simulate this code and with the $display after the non-blocking statement, um, the result of the simulation shows that the $display command was executed in the active events queue before the non-blocking assign update events were executed. So because the $display executes uh, during the active events segment in the events queue, $display will display a as 0, and we from our previous slide we remember that the $monitor will be executed at the end, so it will $monitor will get executed after the assignment of non-blocking 1 to a, so it will report a as 1. Similarly, $strobe will also report a as 1. So this is a typical example where you can see the Verilog stratified events queue taking effect. The next question is making multiple non-blocking assignments to the same variable in the same always block undefined? Making multiple non-blocking assignments to the same variable in the same always block is defined by the Verilog standard. The last non-blocking assignment to the same variable wins. I feel quoting from IEEE 1364 standard. Taking an example here, the non-blocking assignments shall be performed in the order the statements are executed. So A is assigned 0 through a non-blocking assignment, and then it is assigned a 1 to another non-blocking assignment. When this block is executed, there will be two events added to the non-blocking assign update queue. The previous rule requires that they be entered on the queue in source order. This rule requires that they be taken from the queue and performed in the source order as well. Hence, at the end of time step 1, the variable a will be assigned 0 and then 1. So the last non-blocking assignment wins. Okay, moving on to the next question. The question is, what is wrong with adding delays to the left-hand side of any sequence of blocking assignments to model combinational logic? So, so let's take an example code here. Um, it's an error. Um, so now here I have a pound 12 delay on the left-hand side of this blocking assignment. So when we simulate this example code, the output uh, should be updated 12 nanoseconds after the input changes because of this pound 12 delay, and we are trying to model a combinatorial logic. If the input X changes at time 15, and then if the inputs, all of them change during the next 9 nanoseconds, the outputs will be updated with the latest value of X, Y, and Ci. This, if you look at uh, the output here, it got updated at 27 um, because there's a delay of 12 nanoseconds after the first input X change. So, but because the X, Y, and Ci changed again, the calculated output of the sum will use the latest values after the pound 12 delay. This means this change in the CI to the sum took 3 nanoseconds instead of the 12 nanoseconds, which does not match the real hardware logic gate behavior. So this way of adding delays to the left-hand side of any sequence of blocking assignments to model combinatorial logic is not correct. So the conclusion is, when you are designing RTL, do not place delays on the left-hand side of blocking assignments to model combinatorial logic. But on the other hand, if you are writing a test bench, placing delays on the left-hand side of the blocking assignment in a test bench is reasonable, since the delay is just being used to time space sequential input stimulus events. The next question is, what is wrong with adding delays to the left-hand side of non-blocking assignments to model combinational logic? So here is the example code where we are using the same adder and then putting a pound delay on the left-hand side of the non-blocking assignment statement here. If the input changes at x15 and then if all the other inputs, including x, y, ci, all change during the next 9 nanoseconds, the output is updated with the latest values of x, y, and c, which means the change in the ci to the change in the output took only 3 nanoseconds, which is not the correct behavior of a combinatorial logic. So this technique of combinatorial logic modeling by putting bound delays on the left-hand side of the non-blocking assignments is also not accurate. So the conclusion is, when designing RTL, do not place delays on the left-hand side of non-blocking assignments to model combinatorial logic. But if you're writing test bench, then non-blocking assignments are less efficient to simulate than blocking assignments. Therefore, in general, placing delays on the left-hand side of non-blocking assignments for either modeling or test bench generation is not a good idea. Um, the next question is, explain adding delays to the right-hand side of a non-blocking assignment will accurately model combinatorial logic with transport delay. So we take our same example and we put the pound 12 delay on the right-hand side of non-blocking assignment here, and then we simulate this to observe the waveforms. So if you see if the input X changes at time 15, and then all other inputs are also changing over the next time, the outputs are um, the outputs have been queued or scheduled for future assignment, but not yet assigned. So all these input changes result in different values of the outputs, but those outputs are not assigned, but they are skewed because we have to wait for the pound 12 delay. So the always block will again be set up to trigger on the next input event. This means that all input events will queue new values to be placed on the output after a 12 nanosecond delay. So this coding style of adding delay to the RHS right hand side of a non-blocking assignment can model transport delays of combinatorial logic. So in conclusion, when you are designing RTL, delays on the right hand side of non-blocking assignments only when trying to model transport output propagation behavior. This coding style will accurately model delay lines and combination logic with a pure transport delay. However, this coding style generally causes slower simulations. When you're writing test bench, this coding style is often used in test benches where stimulus must be scheduled on future clock edges or after a set delay, while not blocking the assignment of subsequent stimulus events in the same procedural block. The next question is, explain why add delays to continuous assignment statements. So in our example code, we have a continuous assignment statement here, and we added pound 12 delay on the left-hand side of this assignment statement. So when we simulate, you can see that the input X changes at time 15, Y changes at 17, and similarly, X is also changing. So the output on the first change of the X input, the output was originally scheduled to be displayed or output on time 27. Because there are further changes in the inputs, the scheduled output is replaced with the new output because of the changes in the input. So whenever the input changes during this pound 12 wait time, the old scheduled output is replaced with the new one. So we can see that the output is settling only after the last change in the input, which is at time 21. So this is behavior matches the actual logic gates behavior. So this is the best way to model the behavior of combinatorial logic. So in conclusion, when you're designing RTO, use continuous assignments with delays to model simple combinatorial logic. This coding style will accurately model combination logic with inertial delays. Use always blocks with no delays to model complex combinatorial logic that are more easily rendered using verilog behavioral constructs such as case, kz, casex, if else, etc. The outputs from the no delay always block can be driven into continuous assignments to apply behavioral delays to the model. This coding style will accurately model complex combinatorial logic with inertial delays. When you're writing test bench, continuous assignment can be used anywhere in the test bench to drive stimulus values onto input ports and bidirectional ports of instantiated models. So in this slide, we'll discuss the state machine logic about the how to do the modify detector state diagram. So the assumption here is that the input data is streaming in 1 bit at a time, and MS most significant bit is coming first. So so here I name the state names as S0, S1, S2 up to S4. They represent the remainder after division by 5. So S1 means it's a the remainder is 1, S2 means remainder is 2, and S3 means remainder is 3, and so on. S0 means the remainder is 0, and that's when the logic should output a flag where out is equal to 1, representing that the number is divisible by 5. So let's start from the start state. At the beginning, whenever you get a 0, that means 0 is divisible by 5. So the state diagram navigates to S0 and outputs a 1. If you get a 1, then it navigates to S1 state. So the concept here is, because you're getting the MSB first and the data is streaming 1 bit at a time, from whenever you get a new bit, what it is doing is the new bit is either multiplying the old number by 2, or it is multiplying it by 2 and adding a 1. So if you get a bit 0, that means your old number is multiplied by 2. If you get a bit 1, that means your old number is multiplied by 2, and 1 is added to the number. So if you look at the input stream, if you get a 1, and then after that if you get a 0, that means 1 became 1 0, which is 2. And after that, if you get 1 0 1, that means 1 0 became 1 0 1, which is 2 became 5, which 2 became 5 means 2 times 2 plus 1 is 5. So that's the concept. So if you see all the states here, like S1, S1 means the remainder is 1. And when you get a 1 bit in the S1 state, means your next state will have a remainder 3, because you multiply it by twice and add 1 on. If you get a 0 in S1 state, then your next state remainder will be 2, because you multiply by 2 when you get a 0. So if you similarly from S2, you get a if you get a bit 1, that means you multiply it by 2 and add 1, means S2 will navigate to S0, and if you get a 0, S2 will navigate to S4. So that is the basic concept, is to navigate through the remainder values. So similarly, if you are in S4, if you get a 1, you stay in the S4, and if you get a 0, you go to S3. So I think you need to spend some time thinking about this a little bit more, and maybe go over the state diagram multiple times to really absorb or understand how the states are changing based on the input stream of data. So if I just read through the states here, so suppose the input stream is 1 1 0 1 1 0, that means you got 1 S1, 1 S3, then you're back to S4, right? So now 1 1 0, from there onwards, if you keep getting 1, you will stay in S4, and if you do the math, it definitely means that once you're in S4, means your remainder is 4, and you keep getting 1, you will stay in that state. An example is, let's take number 4, and if you multiply 4 by 2 and add 1 to it, you get 4 times 4, 4 times 2 plus 1 is 9, so you stay in the same state, so S4. So from the only way to exit S4 is to get a 0, and that where you go to S3, and from there, depending on 1 and 0, you navigate. If the overall number is divisible by 5, then you reach S0, and that is where you output flag 1. So this is that's how you know that the number is divisible by 5. So friends, please spend some time in analyzing the state diagram more. It's not very intuitive, but definitely it works, and it is a solution to calculate the mod file of the input stream of data MSB first. Thank you very much for listening. Please subscribe. The next question is, um, Design a finite state machine to detect a sequence. Here in this example, we have the sequence as 10110. So the solution is this state diagram, and after reset, you go to S0 state, and from there you you start uh, checking for the sequence. So from S0, if you get a 0, you stay in the same state, and if you get a 1, you go to S1, and that means you have detected the first one. And then from S1, if you get a 1, you stay in the 1 because 1 1 is not the pattern you're looking for. You're looking for 1 0 pattern. So you stay in S1 and then wait for a 0. If you get a 0, then you go to S2. That means when you're in the S2, you have detected 1 0 so far. Suppose in S2 you get another 0, that means you detected 1 0 0, which is not the pattern you're looking for. So you go back to S0, you restart. Suppose in S2, if you get a 1, then you have detected 1 0 1 so far, which matches the pattern, part of the pattern that you're looking for. So you navigate to S3. So in S3, if you get a 0, that means you have detected 1 0 1 0, but 1 0 1 0 is not the pattern you're looking for. But 1010 does match your first two bits of the pattern that you're looking for. So you go back to S2, which means you have detected 1 0 so far instead of restarting. So this is a smart arc because that means you are not restarting, but you are starting at midway where you already detected 1 0 pattern. In S3, if you get a 1, then you have detected 1 0 1 1 so far, so you navigate to S4. Now in S4, if you detect a 0, that means you have detected your pattern, which is 1 0 1 1 0, the full pattern. Then you go to S2. So the reason why you go to S2 is because your pattern begins with 1 0 and it also ends with 1 0. So there could be this pattern could repeat again where you have 1 0 1 1 0 and again 1 0. I mean, counting the last two bits 1 0 as also. So then you go to S2 because in S2 means you already detected 1 0. In S4, if you detect a 1, that means you have detected 1 0 1 1 1, which is not the pattern that you're looking for. So then you go to S1, which means state S1 means you have detected 1 in this case. So this is a solution to detect this particular pattern. So if a pattern is different, then the arcs in the state machines have to be modified accordingly. These topics that we discussed are very essential to crack any VLSI interview. If you are a student or a professional, you will need to master these topics in order to succeed in career. I have tons of experience and material which I'll be posting as time permits. Please subscribe to the channel VLSI Problems and Solutions to get the latest updates. Thank you and have a nice